Dear all, welcome. The topic which we are going to discuss today is about electromagnetic waves, Module 1 for the course PhD 1182 Engineering Physics. So this will be the overview of the course or the syllabus. We will start with the Gauss Law in electrostatics and its differential form of Gauss Law will be discussed. The Poissons and Laplace equations will be discussed, and slowly we will discuss about the Ampere's circuit law, the Faraday's law, and finally we will end up with the Maxwell's equation. So before we enter into the core content of the syllabus, we need to understand some basic concepts related to the course. The first one is the electric charge. The electric charge is actually the physical property of matter that causes it to experience some kind of force when it is being placed in an electromagnetic field. So this electric charge can be either positive or negative. The second thing is electric field is actually the physical field that surrounds the electric charge particles, and it exerts some kind of attractive or repulsive force based on the polarity of the charge. The electric field capital E due to charge Q when it is being placed at point P on an element area at a particular distance r will be given as capital E is equal to the charge Q divided by 4 pi epsilon naught r square, where epsilon naught is actually the electric constant. This relation we should have studied in our lower class. The third thing is electric flux. The electric flux is defined as the number of electric field lines crossing per unit area. Let us consider a material which has the area A. Now if we subject an external electric field capital E, then the electric flux is defined as the product of applied electric field capital E and the area of the material. The applied electric field will have two components. The electric field will have two components, and the normal component which will be inclined at an angle theta with respect to the electric lines of force theta. So in such case the electric flux pi will be given as the product of electric field E capital A area and cos theta. So we have electric flux pi is equal to EA cos theta, where theta is the normal angle of the electric component E. So based on these understandings, let us understand what is Gauss law in electrostatics. The Gauss law states that the total electric flux of the electric field capital E over any closed surface area is actually 1 by epsilon naught times the total charge enclosed by the surface. Let us understand with a small diagram. So we will consider a Gaussian surface and let us assume a charge Q, and we will have a small element area that is ds placed with a distance small r. Now this arrow mark denotes the direction of the applied electric field. So in such case the electric flux pi is given as the integration of E applied electric field ds and cos theta, that is the vertical component of the electric field. So now the Gauss law states that the electric flux pi is actually, we can simplify and we can write it as 1 by epsilon naught times the charge which is being placed within the Gaussian surface. The Gauss law also states that the electric flux pi through the closed surface area will be depends only on the net charge which is present within the surface and not on the location of the charge present on the inside the surface. So let us further explain the concept related to Gauss law. We will shortly review what we have discussed so far. Let Q be the charge which is being enclosed within the Gaussian surface, and ds will be the small element area at a distance r from the charge Q, and electric field capital E is the applied electric field which has two components inclined with angle theta, and we have seen the electric flux pi through the small element ds will be given as d pi is equal to E ds cos theta. Let us consider this as equation number 1. And in the previous slide we have seen about electric field, which is actually due to the charge q at a point P on element area at a distance r is given as electric field capital E is equal to q by 4 pi epsilon naught r square. Let us consider this as equation number 2. Now in equation number 1 we will substitute the relation of capital E. So we have electric flux d pi is equal to q by 4 pi epsilon naught r square ds cos theta. Let us consider this as equation number 3. Now in this equation number 3 we will consider ds cos theta by r square as d omega. So we will consider d omega as ds cos theta by r square to simplify the equation number 3. So finally we will have the electric flux d pi is equal to q d omega by 4 pi epsilon naught. So let us consider this as equation number 4, which is actually the electric flux for the small element ds. Now we need to find out the electric flux for the entire Gaussian surface. So for which we simply need to integrate the equation number 4 whatever we have obtained. So the total electric flux pi for the entire closed surface area is given as electric flux pi is equal to integration of the equation number 4 term, that is d pi. So integration of q d omega by 4 pi epsilon naught. So in this the d omega is actually the total angle suspended by the closed area, and this value will be defined as 4 pi. So we can remodify equation number 5 and we can write it as electric flux is equal to q 4 pi divided by the denominator term, that is 4 pi epsilon naught. So we'll strike out the common terms and finally we will have the electric flux that is equal to q by epsilon naught, which is simply is equal to the Gauss law. So finally we have explained the Gauss law and we have derived the Gauss law with proof. So we have the electric flux pi is equal to q by epsilon naught, that is Gauss law. Now let us consider the case the Gaussian surface will have n number of charge carriers. Let us say we will have q1, q2, q3, q4, etc. In such case the electric flux pi is equal to the sum of all the charge carriers with respect to the epsilon naught. So we have electric flux pi is equal to q1 by epsilon naught plus q2 by epsilon naught plus q3 by epsilon naught and so on. So we can simplify and we can rewrite as summation of q divided by epsilon naught. So hence the electric flux pi is equal to the integration of E ds cos theta is equal to simply the summation of the charge q within the Gaussian surface divided by epsilon naught. Now we will understand the differential form of Gauss law. So we have the Gaussian surface which has the volume V, and if the charge q is distributed over the volume capital V and if rho is the charge density, then the charge q is given as with integral rho dV. Let us consider this as equation number 1. And by Gauss law we have seen in the previous slide, that is electric flux pi is equal to with integral capital E dot ds is equal to q by epsilon naught. Let us consider this as equation number 2. Now we have the charge q, that is equation number 1. We will substitute it in equation number 2. Finally we have integration of capital E dot ds is equal to 1 by epsilon naught with integral rho dV. So let us consider this as equation number 3, which is actually the integral form of the Gauss law. Now in left hand side we will have with integral capital E dot ds. By applying the Gauss divergence theorem we can rewrite this equation as with integral del dot capital E dV, which is actually we are converting the surface integral to the volume integral. Let us consider this as equation number 4, and we will substitute this term in equation number 3. So finally we have with integral del dot capital E dv is equal to the next left-handed side term 1 by epsilon naught with integral rho dv, or neglecting the integration term, we can rewrite this equation as simply as del dot capital E is equal to rho by epsilon naught. Let us consider this as equation number 5. So equation 5 can be rewritten as del dot epsilon naught capital E is equal to rho. So the term within the bracket we can call it as flux density capital D. Hence the equation can be rewritten as del dot capital D is equal to rho, and this will be equation number 6. So equation number 5, del dot capital E is equal to rho by epsilon naught, and equation number 6, that is del dot capital D is equal to rho, or called as differential form of Gauss law. So the next topic is about the Poissons and Laplace equation. We need to derive from the Gauss law. So as you know, the differential form of Gauss law, whatever we derived, is actually the del dot capital E is equal to rho by epsilon naught. Let us consider this as equation number 1. And if capital E is the electric field and capital V is electric potential gradient, then we will have capital E is equal to minus del V. So let us consider this as equation number 2. Now we need to substitute this capital E in equation number 1. So we will have del dot minus del V is equal to rho by epsilon naught, or we will have del square capital V is equal to minus rho by epsilon naught, which is nothing but the Poissons equation we have derived from the Gauss law. So consider the above equation, in which if there are no free charges, then the charge density rho will become 0, which is be given as del square capital V is equal to 0, which is simply, we can term it as the Laplace equation. So thus we have derived the Poissons equation and the Laplace equation based on the Gauss law. So we have some applications of Gauss law. So the uses or the importance or the applications of Gauss law will be as follows. So the Gauss law is actually the fundamental characteristics of electromagnetic theory, and this Gauss law will be used to find the electric field capital E by considering a closed surface area. And the Coulomb's law can be derived from the Gauss law, and using Gauss law the electric field due to charge distribution can be derived very easily. So the next topic is actually the application of Gauss law. There's a small derivation where we are going to find out the electric field at a point due to a charge conducting sphere. For this case, that is the electric field at a point due to a charge conducting sphere, we'll consider 3 conditions. That is, case 1 is electric field at a point outside the sphere, and case 2 is electric field at a point on the surface of the sphere, and case 3 is electric field at a point inside the surface of the sphere. So using Gauss law, we are going to find out the electric field for 3 different cases. Let us analyze one by one. So the first case is case 1, electric field at a point outside the sphere. So let us consider the following. We will consider a spherical shell with a radius capital R, and charge Q is distributed uniformly. So we will explain with a schematic diagram. We will consider a spherical shell with a radius capital R, and center one is origin. So the charge, let us consider the charge spread uniformly across the surface of the spherical shell. Let P be the point outside the spherical shell. So as per our aim of this problem, we need to find out the electric field outside the sphere. So for that, we will consider a point P outside the sphere which has been placed at a distance r. The third one is, let us consider an imaginary circle that is called Gaussian surface, which is drawn with radius r. So connecting the point P, that is outside the sphere, we'll draw a circle that is Gaussian surface. And for this case, we need to find out the electric field at a point outside the sphere. So what will be the electric field at a point outside the sphere? So let us consider it as E1, and by Gauss law we know that the electric flux pi is equal to integration of capital E1 into ds cos theta is equal to q by epsilon naught. Let us consider this as equation number 1. So in this case, the electric field has been considered along the lines of force. Hence the theta will be 0, and hence the term cos theta will be 1. So we will rewrite the equation number 1, that is electric flux, that is will be given as integration of capital E1 into ds is equal to q by epsilon naught. So we will have the cos theta term as 1, and the ds is actually the surface area of the sphere, and we have studied in our lower class the term is defined as 4 pi r square. We will substitute this surface area of the sphere formula in equation number 2, and hence equation number 2 becomes capital E1 into 4 pi r square is equal to q by epsilon naught. So we will have this as equation number 3. So we will rewrite this term to find out the electric field E1. So we'll have E1 left side and bring all of the term right side. So capital E1 is equal to q by 4 pi r square epsilon naught. Let us consider this as equation number 4. So finally we almost reached, or we have almost derived the electric field at point P, that is outside the sphere. Now let us add more detail to the equation number 4. So if sigma is the surface charge density, we have the charge, that is q, is equal to 4 pi capital R square sigma. So instead of q, we will rewrite this the following term, and we will have capital E1 is equal to 4 pi capital R square sigma divided by 4 pi R square epsilon naught. So we will strike out the common terms, that is 4 pi and 4 pi. So finally we will have electric field E1 is equal to sigma capital R square by epsilon naught small r square. So this will be the electric field at a point outside the sphere at a point P. Now let us consider for the case 2, where we need to find out the electric field at a point on the surface of the sphere. So let us consider the following. Let P be the point on the surface of the sphere at a distance small r, and the Gaussian surface lies on the surface of the sphere. So this is the schematic diagram. In earlier case 1, we had capital P outside the sphere, and here we have capital P on the surface of the sphere with the distance small r. So as you all know, we can see very clearly from the diagram, for this case 2, the radius of the sphere and the radius of the Gaussian surface are equal, that is small r and capital R are same. So now for this effect, that is small r is equal to capital R, for this effect we need to find out the electric field E2 at point P, considering capital R is equal to small r. Let us see what will be the effect. Once again let us take the Gauss law. Electric flux pi is equal to integration of capital E2 into ds, that is equal to q by epsilon naught. Let us consider this as equation 1, and once again we will have surface area of the sphere, that is integration of ds is equal to 4 pi capital R square, and hence equation 1 becomes capital E2 into 4 pi capital R square is equal to q by epsilon naught. We will rewrite this term accordingly, that is in such a way that we will have E2 left side and bring all the term right side. We have capital E2 electric field is equal to q by 4 pi R square epsilon naught. This will be equation number 2. Now once again, like in the previous case, we will consider the surface charge density as sigma, and in such case the charge q will be given as 4 pi capital R square sigma. Now we will substitute this q term in equation number 2 numerator. So we will rewrite this equation number 2. So we will have capital E2 is equal to 4 pi capital R square sigma divided by 4 pi R square sigma, epsilon naught. So we will strike out the common terms, that is 4 pi and capital R. So we will have the electric field capital E2 at the point P will be given as the sigma divided by epsilon naught. So for this case too, the methodology is same, the derivation part is same. However, since we had the surface of this sphere in which the Gaussian surface lies on the surface of the sphere, because of which the small r is equal to capital R, due to which the radius term capital R and capital R gets cancelled out, and we will have electric field E2 will be given as sigma by epsilon naught. So this will be the electric field at a point on the surface of the sphere. Let us see the last case, that is case 3, electric field at a point inside the surface of the sphere. So we will consider the following, in which capital P is a point inside the surface of the sphere at a distance r prime, and the Gaussian surface will be lying inside the surface of the sphere. So schematic diagram has been shown here, and where we can see the Gaussian surface lies within the sphere of radius r prime located at the point capital P. Now for this case, case number 3, we need to find out the electric field at the point P. So we denote it as E3, and once again the first step is same. We will consider the electric flux based on the Gauss law, and for which we have to replace the surface area of the sphere, that is 4 pi r prime square. We will rewrite this equation number 1 as capital E3 into 4 pi r prime square is equal to q by epsilon naught. Hence the electric field E3 is equal to q by 4 pi r prime square epsilon naught. Now the thing is, this term will becomes as 0. So E3 will be as considered as 0, because which denotes that the total charge is situated only on the surface of the sphere. It will be either on the surface, and it will have influence if the point P is outside the surface. However, within the sphere there is no charge. Hence the electric field within the sphere will be 0. So we have seen case 1, case 2 and case 3, and thank you all. We'll meet you all in next class. Thank you.